Okay, now I'd like to overview of the FrontISTR functions in this video. So this slide shows the contents of this video too. Okay. So first of all, I'd like to mention the main features of FrontISTR, or what is or は外してください。So this slide shows もう一回いきますね。This slide shows the contents of this video. Okay, so I'd like to start with the features of FrontISTR. Also, I'd like to explain, or I'd like to introduce a general basic information about what the structural analysis simulation is. And actually, the structural analysis treats some physical phenomena. So some mathematical model is explained, and afterwards its discretization such that it can be treated in the digital computers is explained. And once the mathematical model is discretized into the finite element models, now the finite element method is can work as a quite important role at the computer-aided engineering process. And so after this general information about the structural analysis or computational engineering, computer-aided engineering, I would like to add the peculiar information of FrontISTR about its analysis function, element type, and the material type, which FrontISTR can support. Okay, I'd like to start with this slide, which is describing the main feature of FrontISTR. So the first point is that the FrontISTR is a structural analysis program. So its purpose is to obtain the deformation and the stress distribution of the continuum media. So in order to or aiming that purpose, various kind of functions are integrated. Like you can treat the static analysis or dynamic analysis, and for both analyses, linear and non-linearity are can be considered. And the eigenvalue analysis is also a kind of dynamic analysis, but it is a little bit different from the usual dynamic analysis. But anyhow, eigenvalue analysis function is prepared. And also, since we need to consider the thermal stress, in order to do that, we have prepared the function of the heat transfer for steady and unsteady states. Okay, these are the main analysis functions. And the second point is that the in the finite element method, what the digital computer is doing behind the finite element method is that they are solving the very, very large scale linear equations, which is obtained after the discretization or finite element discretizations. So, and most of the computational time is occupied by solving the large scale linear equations. So it's very important to prepare the solvers which solves the such linear equations. And we have considered two levels of parallelization. The first one is that the MPI parallel, which is based on the domain decompositions. Okay, so we decompose a domain into subdomains, and each subdomain is treated as an independent MPI process. And they run simultaneously. Of course, we need to communicate during the computation, but by the domain decomposition, we can run the parallel analysis. And also, in each subdomain, we may consider the thread parallelization. And that is described by the directive. It's a very common use, OpenMPs. So two levels of parallelization are considered when solving the large-scale linear equations. Okay. And so since the large-scale linear equation, which is called the stiffness matrix in finite element method, since the size of the matrix is very, very big, we need to compress or some sophisticated way should be introduced. And in our program, in FrontISTR, block compressed sparse law format is employed. Okay. And the next one is that I have already pointed out, but the FrontISTR can run on various kinds of environments, from Windows PC so far to Linux PCs or PC clusters or supercomputers. And the last point is that it is open source program under the MIT license. You can modify the program as you wish. You can distribute if you want. Okay, so since because of this license, each industry can modify the FrontISTR for their own purposes. Okay. Now this is a very basic explanation about the structural analysis, or this flow shows what the structural analysis simulation is. So if you have some physical phenomena you are going to observe, then that phenomena is modeled by the mathematical expressions. Since the mathematical model is shown or described by partial differential equations, with the boundary or initial conditions, they are called the mathematical models. And if you can obtain the exact solution of this model, then that's the end. But normally, to obtain the exact solution of the governing equations or the mathematical equations, you cannot obtain it. Or otherwise, it's quite difficult to obtain. You need to introduce some approximation and discretize the mathematical model into the algebraic model, such that the digital computer can treat. And depending on what kind of discretization method, like a finite element method or finite difference method, you can choose either of the discretization method. You may obtain the large-scale linear equations. For instance, once you have a shape model which you are going to observe or you are going to obtain its deformation, you may discretize the model into the finite element method, and but you can see that in order to obtain the very high accurate computational solution, you need to use so many number of nodes or many number of elements, and thus the size of the algebraic model would become so big, and so that's why we need to introduce the parallel computers or parallel strategies which can enjoy the potential of the parallel machines. Okay, now I'd like to show in what kind of mathematical model is treated in the structural analysis. So in this slide, for the sake of simplicity, deformation is assumed to be so small, and the mathematical material is assumed to be linear. Okay? And so there are three kinds of basic equations. The first one is the equilibriums. And so please look at the functions shown by the red characters. So the most important one is that the displacement U. Okay? The purpose of the structural analysis is to obtain the displacement at each node. Okay? And the equation of equilibrium describes the displacement state. And with the constitutive equations, which can also be called as a Fuchs law, and the relationship with the strain and the stress, strains and the displacement, the equation system is closed because the displacement U, strain epsilon, and the stress sigma, they are the unknowns. And the equations you are going to solve is the equilibrium equation, constitutive equation, and the strain displacement relationship. So once you can obtain the displacement, this is the main purpose of the finite element method, structural analysis, then you can compute the strain or stress by using these equations. Okay. And of course, we need to consider the boundary conditions to solve these partial differential equations. And okay, this slide is the different expression of the previous governing equations, so I'd like to skip this slide. Okay, and so far I have explained the mathematical model, which is continuous. But when you are going to use a digital computer, you need to discretize of the partial differential equations such that the digital computer can treat. Okay, and in order to do that, we have introduced the finite element method, discretized by the finite element method, and we divide or we discretize the continuum media into many number of elements. Most of the elements have the very simple shape like this, and we consider the element level partial differential equations. And so if we consider on each element the previous mathematical model is satisfied, and then we can construct into the global system, and by doing so, we can obtain the very large-scale linear equation systems like this. And actually, Ku equal F, this is the final linear equation system, which should be solved by the linear equation solvers. And please look at the size of the equation system. So the unknown vector u is the series of displacement. At each node, three components of displacements are defined, ux, uy, and uz. So the size length of the vector u is 3n. N is here the total number of nodes. So in order to obtain the very accurate computational result, we want to use so many number of elements and many number of nodes, then you can see that the size of linear equation system would become so large. Okay? And that is one main reason we need to use the parallel computers. Okay, and this slide shows a little bit more detailed information about the discretization. So I'd like to skip this slide. Okay. Now, okay, once you can use or once you can develop the finite element program, then it can be integrated into one process of the computer-aided engineering. So this flow describes in the design or research and development process. You can start from the equation model design, mainly using CAD, And when you are going to prepare the input data for the finite elements, you need to generate the mesh like this. And also you need to specify the boundary conditions or material constants like this. Then you would execute the finite element program like a FrontISTR. And once you obtain the computational results, like displacements, strains, or stresses, you would visualize and evaluate the analysis results. And this CAE process is repeated in such a way that the final design is obtained. Okay, so far I have explained the general introduction, what the structural analysis is, or the flow of CA process. Now I'd like to focus on the FrontISTR. So this slide shows what kind of analysis functions are supported in FrontISTR. So depending on the type of the phenomena, the functions are described by this slide. So for both static and dynamic problem, infinite deformation or finite deformation theories, both of the linear and the non-linear deformations can be considered. Okay, and as for the static program, if we need to consider the finite deformation, we need to introduce the linearization process by the incremental method like this. Okay, and for the dynamic phenomena, which can be divided into three functions, mainly the transient analysis stands for the dynamic process. So also for the transient response analysis, small deformation theories and finite deformation theory can be considered. And as I said before, eigenvalue analysis and the frequency response analysis functions are also supported. And since we sometimes need to consider the thermal stresses, we need to obtain the temperature distribution. And in order to do that, the thermal analysis function for both steady state and transient state are supported. Okay. This slide shows the type of element. So these topologies are supported in an element. So for the one-dimensional, two-dimensional, and shell elements, and also the three-dimensional solid elements are supported like this. Okay. And these difference of the elements are expressed by the element name by using the numbers like this. Okay. So this is more detailed information about the element type. So I don't go into details for this slide. Okay, and this is the material, type of the material which can be considered in the FrontISTR. So depending on the deformation or small displacement or finite deformation theories, which kind of strains, small strains or large strains, or small displacements or large finite displacements. So by the combining these consideration, we can consider various materials like here. So starting from the linear elastic or elastic plastic, viscoelastic, and the creep. And so functions colored by blue are now supported by the FrontISTR.